turns out that operators have a polar decomposition that models the polar decomposition that we see in R2 or in the complex plane. And so let's just do a quick review of that. It might be a little less familiar in C, so I'll do that. So in the complex plane, any unit complex number has the form cosine t comma sine t if it was written in terms of coordinates like a number in R2. However, in the complex plane, typically we write that as cosine t plus I sine t, where we're using the standard unit basis vectors 1 and I. And then by Euler's theorem, this is equal to e to the it, right? So a given z that we usually think of in terms of Cartesian coordinates is a plus ib, can be rewritten as r e to the it, where r is the magnitude of z, and t is the argument of z. So as in terms of the angle from the positive x-axis. So let me just draw a little picture of a complex number. There we go. Okay, so if this is our complex number z, so we've got here's a, here's b, so this is a plus bi. Then we also have, let's see, taking the unit circle right here. Whoops. Stop that. Okay. Gonna draw a line out to it like this. So for polar coordinates here, let's see, we've got this angle right here is t, and then this length right here is r. Okay. So then when we do multiplication, so say we do z times w, then this is going to be r e to the it, and then for w, let me write w as like s e to the I theta, say. Then what we see is that the magnitudes multiply together, but by the rule for exponential arithmetic, this is I t plus theta. So the angles add. And so what this means is multiplying by e to the it has the effect of rotation by t counterclockwise around the origin. So in other words, if I have, say, this point here as my z, then if I multiply z by e to the I pi over 2, then I'm going to be out here. So this is going to be z times e to the I pi over 2. So I just rotated it this way by pi over 2. All right. So let's see now. So in operator land now, we have the following terminology. So we say that an operator on V is a positive operator if and only if it's self-adjoint. So you can think of this as the matrix of t star needs to be equal to the the conjugate of the transpose of the matrix of T, and that the eigenvalues are non-negative. Okay, and so then we have a theorem, and this is the polar decomposition theorem. It says that for any operator T, there is an isometry S and a positive operator R such that T equals S times R. And so you should think of this as being directly analogous to saying that for any Z, there exists an R positive, well, non-negative, and there exists a unit vector U such that Z is equal to U times R, and that would be e to the it times R in our case, right? Okay. So yeah, so it's common to see this operator R here written as the magnitude of T, like this. Now, notice that's actually sort of bad language and terrible notation, because this like notation looks like norm of T, which you'd think of as a number, and that's actually another appropriate use of that symbol and interpretation of it. And people do talk about the magnitudes of operators when they talk about whether or not an operator is bounded or unbounded and stuff like that. So it's kind of bad. But whenever you have a magnitude given in terms of an inner product, you can always define the magnitude as the square root of the inner product of the thing with its adjoint. And so it's also quite common to write this as the square root of T star T. And then that kind of helps you remember that this is definitely an operator and not a number. Okay, so this, like I said, this comes by analogy with the idea that for an element of a vector space, if you have the magnitude of V given by the sum of the squares of the VKs, then this is the same thing as the square root of the inner product of V with itself. Okay, so that would all be fine and dandy, but then you realize, hey, wait a minute, what the heck is going on here? This guy is the square root of an operator? Yeah, well, it turns out that's actually a thing. So an operator S is a square root of the operator T if and only if S squared gives you T. So there can be all kinds of square roots. So for instance, if you're looking at square roots of the identity, any operator that's its own inverse, for instance, any reflection, will be a square root of the identity. So, okay, so that's what I mean by that square root of an operator in the thing above. So it's helpful to know that square roots are not unique. But every positive operator so as long as it's positive, has a unique square root. A unique positive square root, sorry. So the analogy with numbers carries over perfectly. So if you're interested, this is the content of Proposition 736. And it turns out that P is a positive operator if and only if P looks like T star T for some operator T. And this is the content of 35. So in the present context, this is actually well defined. As the unique positive square root of T star T. Okay. So putting this all together then, thus we can write T as S times square root of T star T, or S T star, T norm, sorry. There we go. So another name for this, by the way, this one here, S being an isometry, is to say S is unitary. And so that kind of conveys the idea that it's like multiplication by a unit complex number. And it also goes in line with the fact that all of its eigenvalues have absolute value equal to 1.